All right, so for today's lab, we are going to be over here on week 4. The nitration of bromobenzene was completed last week from our visit together. And today we are going to be discussing the polymerization of nylon 610, as well as polymerization reactions in general. It's a fairly simple concept, especially going forward into your further advanced chemistry. It's going to be reviewed here on our lab notebook. And then today, since the lab manual is a little bit outdated, we're going to skip forward from reviewing people's pre-labs. So go ahead and consider yourself safe. But remember that next time that when we visit, I'm going to still be checking on people for Thursday for the synthesis of dibenzyl benzyl acetone by aldol condensation. So be prepared so that you are safe and not sorry. And then, of course, if you haven't completed your quiz, then make sure to go forward with that one. And then let me go ahead and get started with our manuals review. Additionally, we will be watching the video here on the polymerization of nylon 610 so you can get a visualization of it. So I'm going to stop sharing and switch over to my lab manual that has notes on it. One moment. I'm going to close my door real quick. Okay, so to get started with polymerization, we're going to go through the concepts firstly. So what is a polymer? And a polymer can be considered a class of molecules or compounds that are characterized by their high molar masses, usually dictated by chains. A lot of things that we know of are like plastics and a multitude of things, from the computer that you're utilizing right now to the table that may be right in front of you. That almost everything can be considered polymers, especially with coatings and other sorts of materials that are throughout our life. So the main idea behind the polymer would be called the monomer, which is the repeating structural unit. It'll be a base unit that we will be analyzing. And because of the large size, additionally, polymers can be considered macromolecules. And in this little notation here, the monomer M, if we have that only as our monomer, and it is in a chain of that single unit altogether, that'd be termed a homopolymer, and that would be the exact same structural unit across by n amount. And when they say n, that is just a variable like x. It is a quantity that quantifies the number of monomers within this homopolymer as an instance. Okay. All right, I see that message, and then we're going to go forward as that a polymer is comprised, of a single unit. So going forward, so if one contains at least two structurally distinct monomeric units, given that it's M1 and M2 separate units like X and Y, for instance, it would be considered a heteropolymer or a copolymer. And as you can see here in a homopolymer, the M subunit N quantifies the quantity of M monomer through a chain. So if you think of rope, a rope would be considered a homopolymer if it is of the same material throughout the rope, singular material. But in a sense of a copolymer, you can think of rope designed by two fabrics, okay? So now you have a copolymer that has multiple monomers within it to create a heteropolymer or copolymer. And these are just basic vocabulary terms towards polymers. So to get you a very brief overview, because polymers are very understated in the organic classes. So in many of your other classes, if you may be taking biochemistry or sorts of biology classes, you can find things like biopolymers, proteins, polysaccharides, terpenes, and nucleic acids. These are all common things that are within the scientific field that are considered polymers. Additionally, the myriad of plastics, elastomers, and fibers that are commonplace are all polymers, and it is just a general statement that is a blanket statement for the idea of polymers themselves. So originally they were called addition and condensation polymerization reactions in order to create them. However, now they have created a new terming of it known as chain reaction polymerization, as well as step growth polymerization. And here are just some of the examples of what they were discussing with regards to real life examples of polymers. So the addition polymerization is known as this because it is from the basis set of addition reactions. So for example, of the self-addition of ethylene molecules, this can yield polyethylene. And so right here you can see the use of ethylene, which is also known as an alkene, okay? By catalyst and or heat, it can create polyethylene, which is a strand, very long strand, which with a subunit set of 10,000 to 30,000. And of course, it can be higher depending on the quantity and quality of your polymer. And so it itself is considered a homopolymer, right? Because all it is the ethylene chains breaking down to single alkanes bonded through a certain subunit set. So then another homopolymer known as polystyrene, you may know of this, is formed by the self-addition of styrene. And so styrene here is a benzyl alkene, and this right here would be a benzene ring attached to a primary alkene group. And then what happens is that the addition reaction occurs at the alkene, and it's stepwise, it adds to itself going forward in a reaction. So all of these you can be considering as like stepwise chain. There's multiple ways to express how polymers are, but you can think of it as building blocks where one unfolds and attaches to the next one. And it's is in a sense like a zipper where everything zips together and it creates a long chain together. And then of course you come back to this idea of N time. So just know that that's a denotation for a quantity. And then there's other sorts of Teflon, tetrafluoroethylene, and plexiglass. There's a lot of real life examples here. But for the sake of time and for your own knowledge sake, I'm going to skip over a lot of these because these are just kind of reiterations of the same concepts that they're talking about with copolymers, saran wrap, by mixing vinyl chloride and vinylidene chloride. And then you create the same thing. It's very straightforward. You either use one thing and it unwraps onto itself in a long chain, or you use two or more things that can unwrap and unchain onto themselves. And so getting down to the nitty gritty, the idea here with the chain reaction can also be known in a sense from like a cationic polymerization, which is found in the polymerization of isobutylene in the presence of a protic or Lewis acid catalyst to give polyisobutylene. So these catalysts, they have to be initiators. They have to start the reaction and or facilitate it. So it just depends on your activation energy and what is actually required in order to do this. But to continue forward, there are some few examples here, like an IR spectrum of styrene, where you can see some of the functional groups that you studied from your IR spectra section, as well as the NMR data here. And then additionally, they add the carbon data, even though that's not really taught in this class, which should be. However, there is some denotations here of the proton spectra, and this will be gone forward into kind of the data set that we'll be discussing later. But for now, let's focus mainly on an important thing here, which is step growth polymerization. And so this is typically involving the difunctionalized monomers. So that just means that it itself, the subset, has two functionalizations, difunctionalized. So for example, a diacid such as terephthalic acid can react with a diol. So this acid group with the carboxylic acid, see it's difunctionalized. There's two carboxylic acids, okay? It can react with ethylene glycol. And so you can see it as a CH2CH2 group bound together, and on each side it's difunctionalized with two alcohol groups. This is catalyzed by the presence of an acid catalyst. You can note this right here by this proton. The H plus just means that there's an acid catalyst, and this can go forward to produce a polyester. So what happens is that the acid group attaches onto the ethylene glycol, the alcohol group, and then they condensate together to create the ester. Okay, so but the polyester, just meaning multiple. And you can see here your ester group is this carboxylic followed by the combination to the ethylene chain. And it continues forward. It continues to reproduce going forward n quantity of times relative to your starting material, the quantity of monomer that you place into this. So chain growth is initiated by the acid catalyzation reaction of carboxyl group. So remember your key words here, the functional groups, carboxylic, this right here, the CO2H of the diacid with a hydroxy function. Hydroxy, also alcohol group attached to your ethylene glycol right here, the HO or OH. And function of the diol. So diol means two alcohols. So the ethylene glycol is a diol to provide an ester. And an ester is the carboxylic acid. However, the proton is replaced there by an alkane group, the CH2 in this case, creating the full ester there. And on the sidelines, you have as well a molecule of water as a side product. So then going forward, the step growth polymerization are much slower. And since they are slower, this is why we need to catalyze the reaction. This is due to the high activation energy, which would be going forward into kind of more of the physical organic chemistry ideas of why this would be high activation energy regarding the stabilization of the two carboxylic acids in resonance throughout the benzene ring. So I'm not going to go too deep into detail there because we'll be treading off track, but that's the reason that they mention the high activation energy. So going forward into the idea of polyamides, these are one type of useful polymer that is also produced by a form of step growth. Now, this is not chain growth, this would be step growth, okay? So from this one, we would know that this is created by diacid and diamine. And so the first example they're going to show you is going to be nylon 6,6. Now, not 6,10, so don't confuse these. This is just the example that they want to show you, okay? So what they do is they take hexane diosic acid and they take 1,6-hexane diamine, and then they react them together, and that will allow you to produce nylon 6,6. And as you can see that they don't have any high requirement here for catalyst to necessitate or facilitate the reaction, because step growth are much more reactive than the chain growth. Chain growth reactions are going to be requiring more of the acid catalyzed, maybe heat. They are just a higher requirement of activation energy. And you can even see here, because the key concept is going to be that resonance stability from our benzene ring here, causing it to require more catalyst or heat to be pressing this reaction forward, whereas here the hexane is only a carbon chain. There's no resonance in there. The only effects you'd have is van der Waals forces, maybe some slight inductive forces there. However, it would not facilitate by resonance the way that a benzene ring would between two carboxylic acids. And so these two can react together in the same fashion and cleave. You can see here the amine group and the hydroxyl group of the carboxylic acid can cleave together in order to create an amide or amide, whichever way that you want to pronounce it. But the key concept is that this amide group can bind onto here on the carboxylic chain, and that way you've created your nylon 6,6. And the quantifier of these numbers, the 6 and the other 6, are going to be from here, okay? So this is a key concept. Hexane, this is the 6th chain in here of carbons. Now, hexane diamine, that's another hexane chain of 6 carbons. So it is 6 carbons on the first part of the monomer, and then the second monomer also has 6 carbons. That's why it's called nylon 6,6, because it is the polymeric chain of 2 6-carbon units binding together. And so this goes forward into explaining further the ideas of what happens in the industrial lab. So I'm going to skip over that for time's sake and allow you to digest that information if you'd care to. But let's get into the real nitty-gritty of what we need to focus on today, and that would be the nylon 610 experiment itself. So this is a polyamide reaction as well that is produced from decane dioic acid. So decane, that means 10, right? So then now we know that we use the same 1,6-hexane diamine with decane dioic acid, creating the nylon 610 instead of 6,6 because decane dioic acid, okay? So additionally, the diacid dichloride can be used, and this is a very good, very strong however, also very reactive. So this is a reason that sometimes we would not use it in lab, because it can be a little too reactive and can also decompose because of how reactive it is. So additionally, to stop the polymerization, you need something to kind of quench or to stop the reaction. And in this case, sodium carbonate can be added to neutralize the acid to prevent consumption of the expensive diamine. And that would mean that it would kind of you have your polymerization running, it's going, it's going, it's going. Toss your sodium carbonate in there to quench it and to stop the reaction. So in the same way that the hexane dioic acid reacted with your hexane diamine, you'll create the same exact reaction. It's very straightforward. It cleaves on both sides. They add together, just like rope, like tying two pieces of rope together, or any other sort of metaphors that you may have for it. And so finally, they also have the decane dichloride, which is also known as sebacoyl chloride. And this is the same thing, okay? Instead, what happens is that the chlorine can actually cleave off and the amine comes in, and then you would have a side of, instead of water, you would have a side of hydrochloric acid. And it's all that matters on that side is that it is more reactive for the dichloride, and additionally that you would create acid as a byproduct, which would also facilitate you requiring more sodium carbonate in order to neutralize the reaction and or to stop it in its tracks. So additionally, they say the reactivity of the diacid chloride is towards nucleophilic acyl substitution, and that is the main concept that we have behind this. So this is a sort of apparatus that they show you, and I'm not going to read you the whole paragraph, but what they want to take here is that you can actually take this SEP funnel and you can string along your nylon rope on the can, and then you can twist the can so that way that your nylon can actually twist over it and have a base to roll onto and create that long nylon rope. So you'll see it here in the video that we're going to watch together, but we're going to skip over this bulk of information just for time's sake. So this is your procedure section, okay? Now, just make sure that you understand the safeties behind this, because you don't want to get any polymers on your skin. You don't want to get any acid on your skin. Additionally, all of your apparatuses here, make sure to list out every piece of glassware with its size, because if you don't have the size, you couldn't walk into a lab and perform this experiment. Maybe you would have a liter beaker instead of a 250 milliliter, and that would be huge. Or you would have a 50 milliliter beaker and it'd be way too small. So you want to be very specific on which glassware that you use. And then we'll go through the procedure of how to perform this in the video. I'm not going to read through all of this just to save you time. And then additionally, they do have an alternate procedure, which is not required. The only procedure required to have in your lab notebook will be the one that's performed in our video. And finally, so here, make sure that under the exercises, that this is your post-lab questions, okay? Make sure that this is at the end of your lab notebook before or after your conclusions. And that's going to be it for this part. Additionally, there's going to be some data as well. So I'm going to stop sharing here. I'm going to save this, and I'm going to come back over to our Canvas portal. Here's your data. Let me know before the end. Most likely the same people who didn't have their name on it before, I'm going to have to add and give you your data. But it's going to be very simple in regards to what you have to do with your data. It's just a subtraction, just to remove the watch glass. And then one moment, let me switch this really quick. Okay, yes. Okay, so at the end of our recording, I'm going to go forward to add everyone onto the data list, because it looks like that there's quite a number. So yeah, if while I'm preparing to pull this video open, if everyone can go through and look, if you are not on the list, because it looks like we have a very large shortage of people currently that were supposed to be on the list. So let's see here. Okay. So we did have some people mentioning that the lab was from the alternate procedure, but let me check really quick. So the primary procedure here, the first procedure would be the diol dichloride. Okay, yeah, so that's the reason, is because in the original procedure they're mentioning the dichloride, and it looks like here we're using the diamine into sodium hydroxide and then diol dichloride. Hold on, it looks like the same. Let me see. So we have sebacoyl chloride, and then let me see. Okay, so let me skip through this video really quick and get over to where we are actually weighing out. And also, you can review the mechanism here of the amine attacking onto the carbonyl, and then the hydroxyl group can actually deprotonate that. Then what goes forward is that the carbonyl is reformed, and then the chloride is a good leaving group. So that is where the mechanism occurs. Okay, and then let's see what we have going forward. Okay, so we have 5% diol chloride in a solution of dichloromethane. And let me check here to see which one that would be. Okay, so yeah, to clarify here, the alternative procedure is what is placed into this video. So the alternative procedure will be what you should have as your procedure. If you had put both of them, I'm not critical on that, so long as that you had this one additionally there. I know it's confusing because there's two procedures. This is additionally why I don't prefer these lab manuals, because there's too much going on there. So one thing here is that the hexane diamine, you can see it actually is suspended in a solution with sodium carbonate. And the reason for that is because when that chloride leaves to create hydrochloric acid, it'll continue to create hydrochloric acid and build up in your beaker. So that is why you have a suspension here of sodium carbonate within your hexane diamine solution. Okay? And then that's just poured over into a beaker additionally. So let's get started over here, and we're going to measure it out through decane dichloro. And then you're going to have a separate graduated cylinder over here. Okay, so you have over here on the side 1,6-hexadiamine, and then on the other side you have your sebacoyl chloride. See if anything important was popping up in the chat. One moment. Okay, I'm going to resend another data sheet that'll have everyone involved. It seems that there was a separate class entirely that was listed there for y'all. So I'm going to email you, everyone here, a separate sheet, and I'll also send it on Canvas so that we can see it. And so kind of missed it here. What actually happened is, so firstly, you have your 1,6-hexadiamine in your solution, okay? It's in the beaker alone. Now, slowly, you're going to want to go forward to add in your sebacoyl chloride. And so he's like very slowly pouring it, and you can see, okay, so now you see the gas there. That's actually chlorine gas coming off. So that happens sometimes when you add an acid into a base that's reacting with it, okay? So now it's gone in there, and the polymer is starting to form. And so now we can use tweezers or some sort of sometimes a paper clip, and it'll start to pull. Okay, so now you can see from here, from the base of it, it's actually creating more and more polymer. And so let me actually come back here and get it's very nice to actually see it very slowly. So you can see in there, there's a globule of polymer. And if you look very closely at the bottom, it starts to pull, and the chain is actually being created at a very, very fast rate. You can't even visualize how fast it's being created. But as we pull it, it goes and it continues to grow. And this is the reason that they have that kind of old school can method, because then you can wrap it on a can and continue to twirl it as it comes out. You can see it's going and going. And safety is important for this reaction because you want to make sure you don't drip out acid on the cabinets and everything. And it's not perfect, right? We don't have an ideal condition here. That's why it's kind of like really chunky in parts and then very spread out in other parts. But primarily, I wanted to show everyone this so that way that you can get a visualization of how to do this. You add the two solutions into your beaker, very straightforward, and then you go forward into slowly pulling out the globules. And that is basically the reaction in a nutshell. Going forward, you can see it just continues to go and go and go. And so now we have our happy polymer. Okay? Still gathering more to get out, a maximum actual yield. And they're even just mixing it together just to really push forward that reaction. So I'm going to skip forward because they're kind of just gathering the polymer created. And additionally, they're going to be pressing it to pull out any excess water, any excess acids. So that would be a common issue. You can imagine on the industrial scale what they'd have to do in order to remove all of the byproduct of acid or water that's created. Okay, and then now here's the hardest part is to remove it from the paper towel. All right, now we have it on our watch glass, and then we can heat it up in our oven. So the machines, I would recommend to add an oven for this one. There's not anything too critical here for machines, and then everything else can be apparatus for this experiment. And even then you can see that it has a fine coating of the polymer left on the beaker. So what we do is we add in a little bit of acid to help facilitate the removal. And this is also a common practice of whenever you're in lab and you have some stained glassware with a very strong base, you can just add acid in order to clean that off. Okay, so now this is dried off. Pull it out, use the scale, do your subtraction, and you're good to go. And then, so this is a sort of more knowledge towards the difference between step growth and chain reactions. And this is good for review for yourself. Otherwise, I would go forward into taking the data that I'll be providing for you. I'm going to go forward and take the list of everyone in our class and then give you some data that you can analyze. Very simple. The real work today is going to be in the post-lab questions. The data, all you have to do is just do your actual yield, and then that's going to be it. Just a simple subtraction. So I'm going to go ahead and close off this video. Thank you for watching.